Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So now, in section 3.3, what we're going to do is actually build on the last two sections. And we're going to specifically, 3.3, what we're going to specifically look at is constant coefficient homogeneous differential equations of order n. Constant coefficient linear homogeneous differential equations of order n, so in other words, of any order. So constant coefficient, linear, homogeneous differential equations of order n. So what this means is we have something along the lines of the following. So the setup is we've got y n, so the nth derivative of y, plus, and then here we could just say p1 yn minus 1 up to pn y equals 0. That's what makes it homogeneous. It's linear because these p's are assumed to be functions not of y but of just x. But furthermore, it's constant coefficient because the pi's are each constants, where each pi is constant. So here we've got basically the same basic setup as we had in 3.1, except that it's higher degree. So then our goal will be to solve the differential equations and initial value problems of this form. Of this form. Now, one thing that I want to cover at this point is a certain bit of notation. So this is the differential operator d. So differential operator d. So d, it represents, so d is a way to represent the derivative with respect to x. And here I mean the ordinary derivative, not a partial derivative, just a classic derivative. So then d squared y, this would represent the second derivative with respect to y, or sorry, with respect to x of y. And just in general, dn of y would just represent y sub n. And we can write things like dn plus p1 dn minus 1 plus pn all times y. And this would be another way to represent the differential equation. Then the characteristic equation for the differential equation is obtained by setting the polynomial differential operator with R in place of D equal to 0. So as an example, let's say we took something like this. So 5 times the fourth derivative of y plus 3 times the third derivative of y equals 0. So then rewriting this in terms of the d, we'd have 5d to the fourth to represent the fourth derivative, plus 3 times d to the third to represent the third derivative. That applied to y equals 0. And so here, this is the differential operator. And so that's going to be 5r to the fourth plus 3r cubed equals 0. And this would be the characteristic equation. Then the use of the characteristic equation is just the same as it was in 3.1. The difference is that we are just now going to have potentially more than two solutions. So then the framework for solutions to the differential equation will be C times e to the rx, where r is a solution to the characteristic polynomial, or characteristic equation, I should say. But we have to make certain nuanced allowances for the sorts of cases that we encountered before. And in particular, we have to allow the possibility that any of the cases that we previously saw may now include higher multiplicity. So note the categories categories of solutions will correspond to what we had in section 3.1. However, wherever there is a solution of higher multiplicity, we disambiguate the terms by including progressively higher power factors of x. For example, the easiest way to see this in action would be this example revisited now. So as an example, let's say once again we were talking about 5 times the fourth derivative of y plus 3 times the third derivative of y equals 0. So then once again we'd be talking about the differential operator polynomial of 5d to the fourth plus 3d cubed applied to y equals 0, which gives us the characteristic polynomial of 5r to the fourth plus 3r cubed equals 0, which we can factor out a factor of power 3 from the r's here. That's going to give us 5r plus 3 equals 0. So then that's going to give us two possible branches of solutions. We're going to have here r equals negative 3/5, and that's with multiplicity 1. Here we're going to have r equals 0, and that's with multiplicity 3. So this one is not different from how we saw it before, but this one is. So the solution, we're going to have y equals c1 times e to the negative 3/5 x. So that's just the same as we saw before. However, now we're going to need to disambiguate all of the powers of 0. So we're going to have c2 e to the 0 x plus c3 x e to the 0 x plus c4 x squared e to the 0 x. But then these are all going to become so these factors are all going to become 1. So what we're going to end up with is just c2 times a constant, or just the constant c2, plus c3x plus c4 x squared. So these extra factors of higher powers of x are how we disambiguate the higher multiplicity factors here. Now let's look at a case like this. So as another example, let's go y triple prime minus 6y double prime plus 13y prime equals 0. So once again, if I rewrite this in a differential operator polynomial form, I'll have d cubed minus 6d squared, representing the third derivative, second derivative, and then first derivative, respectively, with respect to x. So that's it now expressed in terms of the differential operator, which we can denote by d, and then that gives us the characteristic polynomial of r cubed minus 6r squared plus 13r equals 0. Factor out the r, and we'll have r squared minus 6r plus 13 equals 0. Now we're not going to be able to, we can see that we're not going to be able to factor this in its current form, so we'll need to use the quadratic formula or perhaps complete the square. A equals 1, b equals negative 6, c equals 13, and so then that's going to give you r equals negative b plus minus square root 36 minus 4 times a times c, and that's going to be minus 52 all divided by 2a, which is going to be 6 plus minus, looks like square root of, negative 16 over 2. So that gives us an r of 3 plus minus, that'll be 4i divided by 2 is going to be 2i. And then also we have r equals 0. So we've got two different branches here. We've got an r equals 0 of multiplicity 1, and then we've got complex solutions, conjugate pair of 3 plus on the one hand, minus on the other hand, 2i. Now, since there's no higher multiplicity here, we don't have to worry about the disambiguation by means of the x's. And so what that means is that we're going to have y equals, and it's just going to be, say, c1 e to the 0x plus, and then again by the same logic as previously, we're going to have e to the alpha x. So actually, let's go back, denote the 3 here as the alpha, this as the beta, and then it falls into the same framework as what we said before. So it's going to be e to the 3x times c2, so we're just counting up the c's here, cosine, and then 2x plus c3 sine 2x. And then that's just going to be c1, the constant, plus e to the 3x, c2 cosine 2x, plus c3 sine 2x. Okay. Now where we'll have to go with this later is to the world of initial values, and the purpose of all of this is to help help us find the YCs, the complementary solutions to the associated homogeneous equations for non-homogeneous equations. But for now, we're just going to work our way up through the skills that are necessary to tackle the more difficult problems. So let's now take on some initial value problems. So, for example, let's take the initial value problem 9. Y double prime plus 6y prime plus 4y is equal to 0, with y of 0 given to be 3 and y prime of 0 given to be 4. Because this is a degree 2 differential equation, we need 2 initial conditions in order to be able to pin down the values of the 2 constants that we're going to be giving rise to. Alright, so rewriting this in terms of the differential operator, we're going to have 9d squared plus 6d plus just 4 and not and 0 derivative there. All that times y, or applied to y I should say, equals 0. And so then that's going to give us 9r squared plus 6r plus 4 equals 0. Now here we're not going to be able to factor this, so it's going to require us to do something fancier, for example, completing the square or perhaps a quadratic formula. So I'll just go ahead and go with the quadratic formula. So it's going to be with an a of 9, b of 6, c of 4. So that's going to give us an r equals negative 6 plus minus square root of b squared minus 4 times a times c. So that's going to be minus 4 times 9 times 4, which is going to be 144. And then divided by 2a, which is going to be 18. So then that's going to leave us with negative 6 plus minus here. That's going to be equal to, well, in any case, it's 36 times, negative 36 times 3. I know that much because this is 4 times 36. So it's going to be plus or minus 6 root 3 times I, because it's 36 times 3 in there, divided by 18. And so that's going to give us, if we simplify it down a little bit, negative 1/3 plus minus root 3 over 3 times I. And then that in turn is going to give us as the pieces of the complex valued solutions to the characteristic equation. That's going to give us y equals e to the negative 1/3 x times c1 cosine root 3 over 3 x plus c2 sine root 3 over 3x. Now, that's all well and good, except that if I want to use the initial condition here, I need to be able to take the derivative, and it'll be easier to take the derivative if I distribute that. So it's going to be c1 e to the negative 1/3 x cosine root 3 over 3x plus c2 e to the negative 1/3 x sine root 3 over 3x, which takes us to a y prime of c1 times, and now it's going to be negative 1/3 e to the negative 1/3 x cosine root 3 over 3x, and then we're going to take the derivative of the second, leave the first alone, so it's going to be e to the negative 1/3 x here, I'll just write it like this, plus e to that times negative root 3 over 3 sine root 3 over 3x plus c2, and then it's going to be a very similar thing on that one. So c2 times negative 1/3 e to the negative 1/3 x times the sine, sine root 3 over 3x. And then the e part will be left alone, so plus e to the negative 1/3 x times the derivative of the second, which is going to now be root 3 over 3 cosine, sorry, not just x, but root 3 over 3 x. Alright, so now we are going to be plugging in the two initial conditions, a y0 equals 3 and a y prime 0 equals 4. So let's go ahead and cut to that chase. So y of 0 equals 3. That's going to imply that 3 equals, and then here we're going to have, plugging in 0 for x, that's going to be a 1 for the e to the power of. And it's going to be times c1 times 1 plus c2 times 0. So that means c1 equals 1/3. C1 equals 3. So c1 equals 3. If we look at the terms that do not vanish when we plug in a 0 for the x. Okay, now for the y prime of 0 equals 4. So then that's going to give us, looking at it here, we're going to have 4 equals. And now for the c1, let's look at what survives and what doesn't. So we're going to have c1 times negative 1/3. And then on the c2, that's the only one that's going to survive of that one. And then on the c2 side, we are going to have plus root 3 plus c2 times root 3 over 3. Now, because I know that c1 equals 3, that means that that 4 equals negative 1 plus c2 root 3 over 3, which is going to then give us that if I add 1 to both sides, multiply both sides by 3, 15 equals c2 times root 3, so c2 is equal to 15 divided by root 3, but 15 is the same as 5 times 3, but 3 is the same as root 3 root 3. So that means c2 is equal to 5 root 3. And that's going to end us up with, as a solution, y equals e to the negative 1/3 c1, which is 3, cosine root 3 over 3 x plus 5 root 3 sine root 3 over 3x. Okay. And that, of course, should be negative 1/3 x. Now let's try a case of a higher power polynomial, higher order differential equation. So let's try this as example B. Let's go y3, so the third derivative of y, plus 10 y double prime plus 25 y prime equals 0, with the initial conditions of y of 0 equals 3, y prime of 0 is equal to 4, and finally y double prime of 0 equals 5. Alright, so first off, rewriting this in the form of the polynomial differential operator, we're going to have d cubed plus 10 d squared plus 25d all applied to y is equal to 0, which leads us to the characteristic equation r cubed plus 10r squared plus 25r equals 0, which we can then factor out the r and get an r squared plus 10r plus 5, or say 25 equals 0, which here this is going to be r plus 5 squared times r equals 0. Perfect square polynomial right in there, which gives us r equals 0, and that's a multiplicity 1. However, r equals negative 5 is going to be a root of multiplicity 2. So this is now going to give us, as the general form here, y equals c1, and then it's going to be e to the 0x. Then we're going to have c2 e to the negative 5x. However, because this is multiplicity 2, we need a repeated version of this, and it needs to be distinguished from the previous one, so we do that by putting in an x. So it's going to be c3 x e to the negative 5x. Now, if I want to plug in the initial conditions, I need not only this, but I need its derivative, and I need its second derivative as well. So that means and I should actually rewrite this with this term, this being the constant that it is. E to the 0 is just going to be 1. So y equals c1 plus c2 e to the negative 5x plus c3 x e to the negative 5x. Now, we take the derivative, and we take the derivative again in order to get things that we can apply the initial condition to. So y prime is going to equal 0 plus c2 times negative 5 times e to the negative 5x, and then plus c3 times just e to the negative 5x, but then there will be another term, negative 5c3 x e to the negative 5x. Clean this up a little bit. Negative 5 c2 e to the negative 5x, and then plus c3 e to the negative 5x minus 5c3 x e to the negative 5x. Now notice that these are actually like terms, but that's not really going to be too relevant for us for our purposes here because the constants are different, and the constants are actually functioning here as the variables when it comes to plugging in the initial conditions and solving to get the solution. Alright, so now we just repeat. We take the derivative again. That's going to make that positive 25 c2 e to the negative 5x. Over here, we're going to get minus 5 c3 e to the negative 5x. Here, we're again going to need to do the product rule. So from the first bit, we're going to have negative 5 c3 x e to the negative 5x. Oops, sorry, the x was what we differentiated away this time. And then from the second term, we're going to have plus 25 c3 x e to the negative 5x, so that represents us differentiating the second factor. Alright, and then any cleaning up here we need to do. Looks like we have two very like terms right there, so we might as well put those together. 25 c2 e to the negative 5x minus 10 c3 e to the negative 5x plus 25 c3 x e to the negative 5x. Okay, now we've got the three pieces that we are going to be putting into our initial condition. And so let's just cut to the chase and see if we have y of 0 equals 3. Where's that going to lead us? So taking the y equation that we had there, and we plug in 0 for all the x's, and set the whole thing equal to 3, we're going to have 3 equals c1 plus c2 times 1. And then that one is going to disappear. Okay, so be it. Now for the y prime of 0 equals 4. That's going to put us in the situation of plugging in 0 to this one right here. We're going to have negative 4 equals, 4 equals negative 5 c2 plus c3 and then minus 0. Okay, and then y double prime equals 5. So that's the final initial condition. So that means 5 is equal to, now we're going to have 25c2 minus 10c3, and then a 0. Alright, well, we're getting somewhere here. And in particular, if you look at these two, well, first off, this one, we can divide everything by 5, and we'll have 1 equals 5c2 minus 2c3. And here, if you look at these two, they involve the same two variables. So if I just actually add them together, then I'm going to get 5 equals negative c3. So c3 is equal to negative 5. Well, if c3 equals negative 5, then that's going to give me what I need in order to find the value of c2 here. So if I plug that in right there, that's going to be 4 equals negative 5 c2 plus negative 5. Add the 5. Add the 5 to both sides. Don't need that anymore. So I'll have 9 equals negative 5 c2, so that means c2 is equal to negative 9/5. But if that's what I have, then I can plug that in turn up here, and that's going to give me the 3 is equal to mystery c1 plus negative 9/5. So I just add that to both sides, and 3 is the same as 15/5 plus 9/5 is 24/5 is equal to c1. And so then I put the three pieces together and I have y equals 24/5 plus c2, which is negative 9/5 times e to the negative 5x, and then plus c3, which is going to be minus 5x e to the negative 5x. Alright, now before I commit to this, let me do a quick check using some different software. Okay, through some mysterious means, I have confirmed that this is in fact right. I just wanted to make sure that I wasn't going out on the record saying anything wrong to you. Okay, so I'll show you actually at a later point how it is one can check such things as this. But for now, let's go ahead and call that a section. So that was section 3.3, in which we covered the case of constant coefficient linear differential equations of homogeneous form of indefinite degree. All right, join me next time for another episode of Math 256. Bye.